Hi, everyone. Okay, so where do we get started when you're trying to learn about astronomy? Well, it's worth remembering that astronomy is the study of everything in the universe. And so, what that means is, over the course of this semester, we're going to talk about things from the very smallest to the very largest, and everything in between. And so, when you're trying to learn all of the things that you can learn in the universe, it's really easy to get lost and confused. And so, where I want to start today is to say, what are some of the tricks that we have to not lose our bearings? What are the tricks that we have to keep in mind what scale we're operating on when you're working on a certain problem in astronomy? What are the tricks that we have for remembering what context we're working? That's where we're going to start here. Okay? Um, so, for example, all right, if we're talking about the Earth, okay, the Earth is a planet, right? And if we zoom out, now the Earth is just one of 8 planets orbiting around the sun in the solar system. What's the solar system? It's the sun and everything orbiting around it. The sun is a star, right? And so if we zoom out again and look at the whole galaxy, our sun is just one star out of billions in the whole galaxy. And if we zoom out some more, our galaxy is one of a few dozen galaxies in a local group of galaxies, and all of these galaxies are really far away from each other, or at least it seems like it is, until you zoom out some more and it turns out that our local group is just part of the local supercluster of galaxies in which there are thousands of galaxies. And then you zoom out some more and our local supercluster is one of millions of superclusters in the whole universe. So when you talk about going from the very smallest to the very largest, I'm not kidding. Right? And it's really easy, if you're talking about planets or solar systems or galaxies or clusters of galaxies, you're talking about very different sizes, very different distances, very different scales to operate on. And if you forget what you're talking about, it's really easy to lose your context, to lose your sense of scale that you're operating on. So how do we do that? How do we not lose our perspective? Well, let's start simpler than that, right? Let's start from your own backyard. This is the southern sky in winter from Arizona, obviously. And do you recognize anything? Well, maybe you recognize that that's Orion's belt, and after you've gotten a little bit of practice at looking at stars and constellations, then maybe you'd know, okay, if this is Orion's belt, then that means this is the constellation Orion. And maybe you happen to know that off to the left of Orion is the constellation Canis Major. And that bright star right there is Sirius, the brightest star in Canis Major. In fact, that star right there is the brightest star in the whole night sky. Off to the right over here is the constellation Taurus with this bright reddish-orange star called Aldebaran. And so you go to your backyard and you look at the sky and you see, okay, wow, there's thousands and thousands of stars just that you can see with the naked eye just in this one picture, right? Just in this one area of the sky on one night. And so the numbers of stars can get really big really fast if you're looking across the whole sky or if you're looking deep into space. And in fact, the sizes of things can be very different also. We'll see in a minute that the size between Sirius and Betelgeuse, this star here is Betelgeuse in Orion, and this star over here, Aldebaran, right? These 3 stars are very different sizes. And then if you look at, say, that right there, that pinkish orange thing right there, well, that looks like a star, kind of like everything around it. But if you point your binoculars or a telescope at it, it turns out that that's what this is. That one thing that looks like a star is the entire Orion Nebula. That's the name for this. The Orion Nebula is a cloud of gas. That's what a nebula is. It's a cloud of gas. And this cloud of gas is full of hundreds and hundreds of stars. But to the naked eye, you can't see the hundreds and hundreds of stars. It just looks like one object. With the seeing that you can do, with the kind of clarity that you can get from telescopes, though, you can all of a sudden see, oh, you're looking at a completely different kind of object, and it's much bigger, right? Each of these stars, some stars are big, some stars are small, but this nebula is much, much bigger than any of those stars. It's so big that it can contain hundreds of stars inside of it. And these are just the things that we can see with the naked eye or with low-power telescopes or binoculars from our own backyard. If you can look really, really deep into space, you can find images like this. This image is what's called the Hubble Ultra Deep Field. This image was taken using the Hubble telescope, but staring deep, deep into space as far as the telescope can go. And when you look as deep into space as you can, what you find is each of these little objects, each of these little swirl, every speck, every smear, every dot, every little thing in this picture is a separate galaxy. And each of those galaxies is made of billions and billions of stars just on their own. There's hundreds of galaxies in this image, and each of them is made of billions of stars. How many stars do you think that is? Just in this picture, right? The numbers get incomprehensibly large. How do we do it? How do we make these estimates, these measurements of the numbers of stars, the distances to the stars, the nebula, the galaxies? When you're looking at so many objects so deep into space, the numbers get way too big to wrap your head around. How do we keep from getting confused? How do we make heads or tails out of all of this? Well, we've got a few tricks. One of the tools that we have at our disposal for handling these astronomically big numbers is scientific notation. So remember how scientific notation works, right? Scientific notation is all about what power of 10 the number is. So 10 to the 0th power is 1, 10 to the first power is 10, 10 to the second power is 100, 10 to the third power is 1,000. Okay, so if you have 5.3 times 10 to the 3, well, 10 to the 3 is 1,000, so if you have 5.3 times 1,000, that's 5,300, right? So, at this point, the numbers aren't getting too bad, not too big, right? We can wrap our heads around tens, hundreds, thousands, not so bad, right? At this point, we're getting to the point where once the numbers get so big, it's hard for our heads to have an intuitive feel for it. It's hard for our heads to wrap themselves around the concept of these super large numbers. So, if you're dealing with measuring 5,300, you could stick with standard notation. You could say 5,300, or you could switch to scientific notation and say 5.3 times 10 to the 3. Pick whichever's easier for you. Pick the right tool for the right job. At some point, though, the numbers are going to start to get way too big, right? 10 to the 4 is 10,000. So let's say, for example, if you have the number 89,000, maybe you can wrap your head around the concept of 89,000 of something, and maybe you can't, right? So whether the size of the numbers gets too big here or later or before, whatever. At some point, the numbers get so big that you're writing a whole bunch of zeros and writing commas to separate the zeros, and it becomes more trouble than it's worth. You're going to want to just switch to scientific notation where you can say, all right, so this is 8.9 times 10 to the 4. Okay, we do this for two reasons. Not just because we don't, with scientific notation, you don't have to write all the zeros and commas for really big numbers. But scientific notation does something even better for us. Scientific notation is a code that tells us important information about this number, right? And here's the nice thing. The most important thing in this number is the power of 10. Because the power of 10, that little 4 there, that tells us how big this number is. That tells us what scale we're operating on. What kind of a number is it, right? 10 to the 4 is what? 10 to the 4 is 10,000. 8.9 is a few of something, right? If I had 8.9 of something, I would have a few of something. So how big is this number? Well, it's a few tens of thousands, right? It's a few times 10 to the 4. How big is this number? Well, 5 is a few, so this is a few thousand. Before you start dealing with the details, right? Before you start worrying about the actual value of the number, the details of some scientific or mathematical problem, before you start getting bogged down in the details, the first job is just look at this number and go, well, about how big is it? Right? Oh, it's a few thousand. Oh, it's a few 10,000s. It's a few tens of thousand. Because reminding yourself how big the number is we're dealing with. What kind of a number are we dealing with? What scale are we operating on? That can help us from making simple mistakes. And that's going to help us out a lot in the long run. Right. And scientific notation can also help with very small numbers. You can say, oh, 10 to the negative 1 is 1/10. 10 to the negative 2 is 1/100th. 10 to the negative 3 is 1/1000th. So if I gave you the number 0.0066, and I asked you, well, how big is that number? Well, you'd look at the decimal and a bunch of zeros, and you'd say, that's a small number. Okay, you're not wrong, but give me a better idea. Give me a better guess as to how small that number is. Well, if you switch into scientific notation, you'd say that that number is 6.6 times 10 to the negative 3. So that basically is, 6 is a few. 10 to the negative 3 is a thousandth. So how big is this number? It's a few thousandths of something. All right? So yeah, it's small, but now we have a sense of how small. We're in the thousandths. Not the hundredths, not the millionths, but the thousands. Okay. And that'll help us get a sense of how big or how small the number is we're playing with. Okay. I've got a couple of asides here to tell you and to show you ways that we can use this to make our lives easier. Because when you're putting numbers in scientific notation, in a calculator or in a computer, a machine understands. Machines have been programmed since the advent of computers. Computers have been programmed to deal with scientific notation differently, in a way that they can process these numbers faster. So they use that. What they do is they use this machine code, or I'll call it the E notation, where if you're putting, where's my mouse? There you are. All right, if you're taking 5.3 times 10 to the 3, if you were putting that into a computer or in your calculator, instead of writing 5.3 times 10 raised to the third power, you can do this in your computer much faster. All you need to put in is 5.3E3. And the E stands for times 10 to the power of whatever you put after it. Right? So if you put into the computer 5.3E3, the computer will understand you mean 5.3 times 10 to the third power. If you put in 8.9E4, the computer will understand that that is 8.9 times 10 to the fourth. Okay? So there are fewer buttons that you've got to type into your computer and less chance that you're going to make a mistake or that the computer misunderstands you and does the math wrong for you. Okay, so this is super handy. Now, how you do this, how you put the number in E notation on your calculator or on your computer is a little different. Some calculators use different buttons. So the first thing you're going to want to do for the homework is figure out where the E button is on your calculator. So let me pull up a calculator here on my computer and show you what it would look like here. On my calculator and on a lot of calculators, the E button is actually called EE, double E. I don't know why. I honestly don't know why. Probably so that you don't get it confused with lowercase e here. And here's where you want to be really careful, okay? In order to put numbers in scientific notation, we're not going to use the lowercase e. Why? Because lowercase e is actually a constant. It's what's called Euler's number. And e, if I click the E button, that little e stands for 2.71828, etc., etc., etc. It is a transcendental number, kind of like pi. You know, the way that pi stands for 3.14159 and so on. E stands for 2.718 and so on. Okay? That's not what we want to do here. So just on your calculator, make sure that you're pushing the right E button. Okay? I'll clear this out. So if I wanted to put in 5.3 E3, and my calculator still puts it as little e, not capital E, just to make it more complicated, I guess. But I pushed the right button, so it'll do it right. And if I put into the calculator 5.3 EE3, and I hit enter, it'll understand that I meant 5300. Right? If I put in 8.9 EE4, it'll know I meant 89,000. And if I put in a negative, here's where we want to be careful. Because if I wanted to put in a negative here, like say 2.1 times 10 to the negative 2, all right, 2.1 EE2, and we're not going to use a minus, because a minus means you're subtracting. We don't want to be subtracting a number, we just want it to be a negative 2, so we're going to hit this button to switch the positive 2 to a negative 2. On your calculator, it's probably going to be the same way, where if you're wanting to put a negative 2, use this button, not the minus, because we're not subtracting, we're just making it negative. All right, and then I hit enter, and the calculator knew that 2.1 E minus 2 is 0.021. Okay? Okay. On your calculator, figure out where the EE button is. It might not even say EE. It might have a different symbol like, it might have a symbol like 10 to the X or something like that. So, if you know where that button is, great. You know what to do. If you're not sure about what to do on your model of calculator, I think the best thing to do is come and talk to me, show me your calculator, and I can help you out with that. Okay? Probably the best way to do it. Okay. So, one more thing. You can also use this E notation in a spreadsheet. So if you're having a spreadsheet do math for you, you could say 5.3 E3. And again, I'm going to use a lowercase e because the spreadsheet knows what I mean. And if I put in 5.3 E3, it'll either leave it as scientific notation. It'll just leave it as 5.3 E plus 3, so 5.3 times 10 to the third power. It'll leave it in this notation scheme. Or I could highlight this. If I right-click and go to Format Cells, I can have it change. The program is set up to give me the number in scientific notation. If I just want it as a straightforward number, I can click Number and click OK, and OK, it converted it from scientific notation into standard notation. We can also go the other way around, right? Right-click, format cells, switch me back to scientific notation, and it'll convert it for us. Pick the right tool for the right job. Sometimes you want scientific notation, sometimes you want standard notation. Now you know how to do both. Great. All right. One more aside, real quick. When you're doing any scientific research, dealing with significant digits is very important. What are significant digits? Significant digits are a decision about where to round your number, how to give me an answer, how to give me a numerical answer, but round it so that the accuracy of your value is honestly reported. Now, that's a little weird. It's a weird way to say that, your number needs to be honest. Aren't all numbers honest? Well, not really. Significant digits are about honesty, and they are about intellectual integrity to report a number, but to tell everybody how accurate your number is, how precise or how sloppy your number is. Okay. And the rule for significant digits is your answer cannot be more accurate than the least accurate of the measurements that went into getting that answer. So let me give you an example. All right. Let's say you did an experiment and you need to measure two things. In order to calculate something, you need to make two measurements and then take those two measurements and divide them. So the first measurement you made is 7.1. The second measurement you made is 121.5. You take 7.1, divide by 121.5. What do you get? But you know what? Let me show you in the spreadsheet, actually. Because you can program a spreadsheet to do the math for you. So let me move this over here. So let's say, okay, I made one measurement. What measurement did I make? Okay, 7.1. I made my second measurement, 121.5. Okay, and now I'm going to divide those two numbers. I mean, yes, I could do this on my calculator, but I want to show you how you can do this in a spreadsheet when this becomes handy later. Here's how you get a spreadsheet to do math for you. The first thing you do is equals, right? If you start that cell with equals, that tells the program you're going to do this math for me. Okay? And so I'm going to have the program grab 7.1, right? 7.1 is the number in cell A1. So if I say A1, if I just type A1, the program knows, okay, go to cell A1, grab that number. And then I'm going to divide by this number, right? 121.5. So I've programmed the spreadsheet to grab the number in A1, divide by the number in A2. And and if I hit enter, okay, I've divided those two numbers. And actually, I typed those numbers into my PowerPoint here. So let's look at this over here. Right, I move my number over here. Your calculator might do the math and give you all of these decimal places, but you're not going to report that, because if you reported that your answer was this number, what you are implicitly saying is you did this experiment so well that you can justify reporting 11 decimal places. And honestly, that's probably not how good the experiment went. How do you know? Look at the significant digits of the numbers that you measured, right? In order to calculate this number, you had to measure 7.1 and 121.5 and then divide them. Okay, how many significant digits does 7.1 have? 2. It has 2 significant digits. How many significant digits does 121.5 have? 4. All right, so 7.1 has 2 significant digits. 121.5 has 4 significant digits. Which one has less significant digits? The 7.1 does. Okay, so if the least accurate of your measurements If the measurement with the least number of significant digits is 2, then you can't report 9 significant digits. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 significant digits. You can't report 10 significant digits when this number was arrived at by making a measurement that only has 2 significant digits. If you tried to say, here's my answer with all these numbers, everybody would look at that and go, you're lying, right? You're lying about how accurate your answer is. You've got to round, and you're going to round to 2 significant digits, right? Your answer has to be rounded to 2 significant digits because 2 significant digits is all of the accuracy that you can justify given the accuracy of the measurements that went into getting that answer. Okay. So where do we round? Where should we round this number to 2 significant digits? How do you count this number to 2 significant digits? And here's where sometimes it's not as easy as it looks. Is that 0 there? I mean, are these zeros significant? Do they count, or should we ignore them? And honestly, the easiest way to do that, the easiest way to round to significant digits is convert to scientific notation, right? Convert this number into scientific notation, and it becomes 5.84362139 times 10 to the negative 2. I haven't rounded yet, right? I've still got 10 significant digits, but the zeros disappeared. Well, if you convert your number from standard notation into scientific notation and the zeros disappear, they must not have been significant. If you convert into scientific notation and the zeros don't disappear, then they were significant. But if they disappear, they're not significant. You didn't need to count them. All right. So we've got the job much easier for us now. We need to round this to 2 significant digits. So 5.8, done. Right? There we go. Right? It's just 5.8, right? Drop the rest of the digits. You cannot justify these digits, right? What I'm saying is, your answer, what we know for sure, what you know for sure, based on your measurements, is that the best answer you can get is 5.8 times 10 to the negative 2. What's the next digit? 5.8 what? You don't know. Your measurements weren't good enough to say confidently what the third digit is. So you report the number to the best of your ability, right? Round to the number of significant digits that you can defend, that you can justify given the value of your measurements, and then say, okay, there's my answer. If you wanted to get the third digit, 5.8 what? Well, then you would need to remeasure with a better measuring device that can give you more significant digits. And then you could justify more significant digits in your answer. It's about, no measuring device, no scientific measuring device is perfectly precise. They all fail at some level of accuracy. I mean, the more accurate, the better, but they all fizzle out at some level, at some scale. So if this is the best you got, then this is the best answer you got, right? It doesn't make the answer wrong. It makes this answer right because this is your answer. This is your answer honestly reported to say, here is my answer given the measurement that I made. It is both true and honest. You're never going to write down this, however many arbitrary decimal places your calculator spits out. You're always going to look at that big number, that big spray of decimal places, and say, where do I need to round? Where do I stop? Well, look at the measurements that you got, and that'll help you decide. Okay. One of the other ways that we have for making heads or tails out of these huge distances, huge sizes, huge numbers, is that we invent convenient unit systems, right? If you're measuring distances around the universe, you're not going to use miles or kilometers because the numbers get really big really fast. Switch to a unit system that makes the numbers manageably small. So, for example, in astronomy, you can measure distances using the astronomical unit. What is an astronomical unit? Well, an astronomical unit is the average distance between the Earth and the Sun. Right? How far away is the Sun from the Earth? 1 AU, 1 astronomical unit. And then if you want to know, well, how big is that in miles? Well, 1 AU is about 93 million miles, or 150 million kilometers. Now, talk about lots of zeros and commas, right? We're already in the scale of hundreds of millions of kilometers, and that's just the distance from the Earth to the Sun. You know, the Sun is basically in our own backyard, and we're already at these huge numbers. So what are you going to do? Well, you could convert kilometers from standard notation into scientific notation. You say like, okay, 1.5 times 10 to the 8 kilometers. That's nicer anyway, nicer than all the commas and zeros, but why juggle these huge numbers when you can say, how far away is the Sun? 1 AU. 1 is a much nicer number to deal with. And so when you measure the distances around the solar system, you know, the distance from the Sun to the Earth, the Sun to Mars, the Sun to Jupiter, when you're measuring distances around the solar system, we're not going to use miles or kilometers because the numbers get huge. We're going to use astronomical units because the numbers stay small enough that we can wrap our heads around them, small enough that we can keep a handle on what we're doing. But that's inside of the solar system. Once you get outside of the solar system and start talking about distances to other stars, astronomical units aren't big enough. Right? Here is, let's look at this picture here, right? Here's a little cartoon of the Big Dipper. Here's the Big Dipper. And if you look at the third star in the handle of the Dipper, that bright star right there is Alioth. Alioth? I think that's how it's pronounced. And then this star right next to it, which is called 78 Ursa Majoris, it doesn't have a nice name like Alioth, it's just 78, meaning it's the 78th brightest star in Ursa Major. These two stars are a light year apart. And that's just that far in the Big Dipper. So, if you're talking about the distances between stars, we're not going to use astronomical units. We're going to use light years because these numbers, you know, talking about the distances between stars, oh, that's 1 light year. Okay, 1 is a nice number. What is a light year? What does it mean, though? What is a light year? A light year is the distance that light travels in a year of time, right? Light travels at a constant speed, the speed of light. And so in 1 year of time, light will travel 1 light year. That's the definition of a light year. But how big is a light year? Well, it's 9.46 times 10 to the 12 kilometers. What is that? 9.5 trillion kilometers? 9.5 trillion kilometers is just that little distance there, right? Or about 63,000 astronomical units, right? Once you get to talking about distances between stars, do you want to juggle billions of kilometers? Do you want to juggle tens of thousands of astronomical units? Or one light year? Yeah, let's do 1. 1's an easier number. So when you're measuring distances between stars, we'll use light years. Or, for reasons that we'll get into in a later video, we also measure the distances to stars in a unit called a parsec. So a parsec it's a little more than 3 light years. So, 3 light years, 1 parsec, those two numbers are about the same. 3 and 1 are about the same. So if you're talking about, distances between these two stars, say, oh, okay, well, if these two stars are 1 light year, these two stars are probably like 3 light years apart. So these two stars are maybe a parsec apart. Something like that, right? These numbers stay reasonably small now, which is nice. So sometimes you'll measure a distance in light years. Sometimes you'll measure a distance in parsecs. Pick the right tool for the right job. And how do you know which one's the right tool? We'll get there. We'll get into those issues another day. Okay? So, all of these different units of measurement are all about picking the right tool for the right job, right? If you're talking about distances around the Earth or distances around the moon, stick with kilometers or miles, right? Because the numbers don't get too big. The Earth is thousands of kilometers in radius. Not too bad. The numbers aren't too bad there. But once you start talking about distances around the solar system, kilometers are too small, so we switch gears to astronomical units, right? If you talk about the distance from the sun to Mercury, Venus, Earth, Mars, all the way out, right? These numbers are the distances from the sun to that planet, right? 1, 5, 9, 30, 40, about 40, right? Even the really distant objects like Pluto at the very edge of the solar system, they're billions and billions of kilometers away, but I don't want to write billions and billions. I'll just write 39.5. Out to the edge of the solar system, the numbers are reasonable numbers of astronomical units, right? But then if we zoom out some more and start looking at the neighborhood around the sun, right? Here's sort of a zoomed out, here's a cube of what the galaxy looks like around near the sun, right? So here's the sun, and all of these stars near the sun are within a few light years or a few parsecs. But if we zoom out some more and look at the entire Milky Way galaxy, we don't live at the bright center of the galaxy. We're kind of out here in the nice quiet suburbs. And the center of the galaxy is 28,000 light years away. The whole diameter of the galaxy is about 100,000 light years. So the distances to nearby stars are a few light years. The distances to far away stars in far reaches of the galaxy are thousands of light years. So again, we're operating on very different scales, very different sizes and distances. I promised before that you can also use this trick for talking about sizes, right? If the Earth is, about 6,000 kilometers in diameter, okay, Venus is about the same size as Earth, Mars is smaller, Mercury's even smaller. So, if you're talking about planets like the Earth, then yeah, you could measure their sizes in kilometers. It's just going to be thousands. Not too bad. But if we zoom out and look at the Earth relative to Jupiter, Jupiter is much bigger than the Earth. I don't want to measure the radius of Jupiter in kilometers. The numbers are annoyingly big. So what am I going to do? Invent a unit that makes life easier. So I'm going to say, let's define that the radius of the Earth is 1 Earth radius, right? 1 Earth radius is the radius of the Earth. What's the radius of Venus? Oh, a little less than 1 Earth radius. What's the radius of Mars? Well, looks like the radius of Mars is about half the radius of the Earth, so the radius of Mars is half an Earth radius. Okay, the numbers are nice there. But then you zoom out and say, well, how big is Jupiter? Well, it turns out that Jupiter is about 11 times the radius of the Earth. So what's the radius of Jupiter? 11 Earth radii. Right? 11 still a number I can handle. But if we zoom out some more and start looking at stars, right? Here's Jupiter. Here's this Wolf 359 is this little red star that's a few light years away from our solar system. Here's the sun. The sun is much bigger than Jupiter, right? I'm not going to measure the size of something big like the sun in Earth radii because, again, the numbers get too big. We're operating on a different context. Now we're talking about stars, not planets. So if we're talking about a different context, if we're operating on a different scale, let's make a new unit. How big is the sun? The sun is 1 solar radius. What is a solar radius? It's the radius of the sun. Here's Sirius, right? Sirius is the bright star in Canis Major. It's the brightest star in the night sky. What's the radius of Sirius? Well, it looks like Sirius is about 2 times the radius of the sun. So what's the radius of Sirius? 2 solar radii. Right? If I told you that Sirius's radius was blah, blah, blah million kilometers, you'd think like, well, that's big. I'll make up a number that's kind of close. Okay. Sirius has let's say, I'll tell you Sirius has a radius of 5 million kilometers. And you'd go, 5 million is a big number. That means Sirius must be a really big star. And I'd say, well, it's bigger than the sun. But if we zoom out again, here's Sirius compared to Aldebaran. Aldebaran, remember, is that bright reddish-orange star in the constellation Taurus that we looked at earlier, right? Aldebaran is huge compared to Sirius. But if we were talking about just huge numbers of kilometers, you're going to get lost in the weeds. It all just sounds like big numbers. So let's not do it. Let's say, how big is the sun? 1 solar radius. How big is Sirius? 2 solar radii. And then say, well, how big is Aldebaran? Aldebaran is hundreds of Earth radii. Right? Hundreds, still a number that we can handle, but it tells us, it's hundreds of times the size of the sun. That's a big star, which is why stars like Aldebaran are called red giants, right? They're called red giants because they're red and they're giant, much bigger than the sun. Aldebaran is a red giant, but if we zoom in again, Aldebaran is small compared to Betelgeuse. Betelgeuse is what you call a red supergiant because it's red, reddish orange, and super huge compared to Aldebaran, Sirius, and the sun, right? The radius of Betelgeuse is thousands of solar radii. It's thousands of times bigger than the sun. And Betelgeuse is not the largest star in the galaxy. There are a few stars that are even bigger, even redder red supergiants. But Betelgeuse is one of the biggest. So again, how do we keep from getting confused? You cheat. You cheat and you make up a unit that makes your life easier. You're talking about the sizes of planets? We'll talk about the sizes of planets in Earth radii. The numbers stay nice. You're talking about the sizes of stars? We'll talk about their sizes in solar radii. Because I know what 1 solar radius is. It's the radius of the sun. And even the biggest stars are thousands of solar radii, which is huge, but the number is nice and manageable. Pick the right tool for the right job, like I keep saying. Right? If we zoom out even more, this is an image of the Andromeda Galaxy. This is the nearest galaxy to our galaxy, to the Milky Way. Remember how I said stars on the far side of our galaxy are thousands of light years away? Andromeda is 2 million light years away. Right? Andromeda is not a star in our galaxy. It is an entirely separate galaxy made out of billions and billions of its own stars. Right? Like I said, there are huge stars. But when you look at even the biggest stars as viewed from really far away, you can't pick out the individual stars. In fact, you might think I'm lying because you say, well, I can pick out these individual stars. Those are in the foreground, right? The stars that you can see in this picture, those are nearby stars in our galaxy in the foreground of this image. And then all the fuzzy stuff in the background is Andromeda and these 2 smaller galaxies that are right next to Andromeda, much farther away. So far that you can't see the individual stars anymore. All you see is billions of stars glowing all together, making this whole galaxy. A completely different context, right? If we're talking about faraway galaxies, they have distances of millions of light years. And so we're going to get some practice talking about these huge numbers, different contexts, so that whether we're talking about small things like planets or huge things like galaxies or even bigger things like the distances to other galaxies, we need to train our brain to be able to pick the right tool for the right job, shift gears when we need to talk about big things, small things, close things, far things, all those kinds of different contexts that we're going to be doing all semester long. Right? All of these tools are a way for us to understand the universe. When you talk about these faraway galaxies, like I said, Andromeda is the nearest galaxy. It's only 2 million light years away. Right? When you talk about galaxies, 2 million light years is right next door. These galaxies in the Hubble Deep Field, these are hundreds of millions, and a lot of them are billions of light years away. Billions of light years to the distant, I think if memory serves, that galaxy right there is the most distant galaxy in the background of this image, and it is several billion light years away. So when you're talking about faraway galaxies halfway across the universe, now you're talking about billions of light years distance from us. So again, we have these tricks, these tools, using scientific notation, using calculators and e-notation, and picking convenient unit systems. All of these are tools to just not get totally overwhelmed and confused by these giant numbers. Right? They're tools for us to cut through the details and get to the most important thing, which is understanding what's really going on out there in the universe. Okay. I think that's a good place to stop. So, if you are in the in-person class, then you can stop there, and we will pick it up there on the next item in the module. If you're in the online class, then you're ready to open up the textbook and start on tool number 1. And once you've completed tool number 1, we'll pick that up with the next video. All right? Okay. Have a good day, everybody. Talk to you later.